Just make sure this doesn't fall over.
Make sure it doesn't fall over, James.
Yeah, make sure it doesn't fall over, James.
Oh yeah, you gotta tilt it. You gotta turn it that way.
I just got to be able to see me, not the whole board.
Okay.
I'm gonna McDonald's the board. Remember?
As long as it's CG.
Okay. Look. Today, this is the. I think This is gonna be the final stuff that's on your test, which is torque. Okay. Now, how do you make something spin? You have to apply a force to spin it, right?
Yeah.
Okay. Headphones out there. Ross.
Loss is what
Spencer Jacobs. You have to apply a force to make something spin. Well, when you make something spin and you apply a force to it, it's called a torque. Okay? Now, you probably have heard of torque as like engines. And it is. It's related to spinning. But today, we're just going to get acquainted with the definition and familiar with the concept of torque.
Oh, James.
So today, torque is what makes things spin. An example of that would be like opening your door. Okay, if you apply a force over a distance through an angle, sine angle here, and we're back in degrees today. We're back in degrees, James. Then you create a torque. You spin something. Essentially, I'm making the door spin around its axis by opening it and closing it, right? Well, how many of you ever been on a seesaw on a playground?
Definitely.
Nobody's ever been to a playground?
I love them.
Okay, back in the day, when we used to be dangerous and we didn't have
You would jump off right at the end.
we had asphalt playgrounds, we had metal jungle gyms, we had 2x4 seesaws. We used to bounce on this thing called a seesaw. And that's what's on your desk is a seesaw. And a seesaw is a perfect example of torque. Because what are you doing? You're basically making it spin, but the other side stops it and spins it the other way. Force times a distance, which is radius, r, times an angle. Okay? So you make something spin by applying a torque. Flip over to page 209, and you can see that if you apply a wrench is another example of a torque because it's basically like a seesaw. Okay? Ryan, this wrench would be hooked into the pivot point. A seesaw has a pivot point, right? Well, a wrench is like half of a seesaw. A door is basically half of a seesaw. So if you press on one end of it, it moves. And the further away you get, the easier it gets. I'll show you. Before we get into the seesaws, I'll show you what I mean.
Ow.
I have here 2 sticks. Both of them weigh 500 grams. Okay? This stick is 500 grams. This stick is 500 grams.
One's hollow.
No, this is not hollow. This is solid. This is 500 grams. This is also 500 grams. This one feels lighter. Why does this one feel lighter? It's like a sword.
Smaller. It's a fencing
Because
stick.
all the weight is at the end.
Oh, I didn't even see
In this
that.
one, the weight is evenly dispersed, but all the weight here is at the end. So the end of it feels lighter. But if I move the weight all the way to the end of it, it's going to feel what now?
Heavy.
Heavier than this one. But in
Oh,
fact,
thanks,
it's
Ben.
still 500 grams. But all the weight is concentrated here at the end. It's moving it over a distance, and it's generating a torque. And I'm having to use my muscles to keep from spinning. Okay? So I'll pass this down. Make sure you don't smack anybody. Okay? So, if you move this weight, you're changing the distance. You can feel it getting heavier, but it's not changing its mass. You're just moving the weight out to the edge.
It's less torque.
It's creating a torque.
It's heavier.
It's more torque.
Okay? It's creating a torque in
Now
there.
it's average.
So there's the equation. It's a Greek T. Torque equals force times r, radius, or distance, times sine theta. Here we go question.
Do we have to draw the feet?
All right. Just a second. Let's not get to the feet yet.
Okay.
Right now, after you played with the rods there, I want you to go to the meter stick. We're going to do a game with the meter stick. The meter stick is a seesaw.
What's that for?
We're going to balance the meter stick. Right now on your marker there, I want you to bounce the meter stick without any pennies on it.
James, bounce without pennies.
Without pennies.
Put it perfectly halfway.
Yep. Should be at 50 centimeters big.
It's a little bit different. The
So you're
ward.
going to have to clear things out of the way.
Come on, Hinkle.
Best you can. Not on your finger, Brady, on the marker.
Can I do it on my nose?
Okay. The mass of a penny is 0.0025 kilograms. I want you to put 1 penny on the left, 4 pennies on the right.
I got the left one. How far down? All the
Okay.
I had it balanced.
What is the weight of Newton in 1 pennies? 1 pennies in newtons.
way? All the way down, James. At the end.
Mass times gravity, right? Okay. What about the weight of 4 pennies? Mass times 4 masses times the gravity. From the middle. What is your distance for the 1 penny? What is your distance for the 4 pennies?
Halfway. So 50.
Are they the same? They are not the same. You can put them anywhere you want, but you got to get it to balance.
We gotta make them balance.
Move the 4 pennies.
You gotta bring them closer.
You can put the 1 penny at the end if you want, but move the 4 pennies until the thing balances. You can stack the 4 pennies on top of each other. Stack them on top of each other like I have on the board. Because it's easier to calculate. You're doing too much math. Okay. From how far was the penny? All the way to the end? So the 1 penny is 50. So where's your 4 pennies at? On 60. So it is 10, right? So if it's 10 centimeters from the middle, all right, and you have 4 times the mass, then it would be 0.10 meters times 4 times the mass times gravity. That's the torque on this side. Torque on this side for the 1 penny, the weight of the penny, mass times gravity, times whatever your distance is. What is that, 50? Is it all the way at the end? 50. 0.50. So the numbers should equal the same if it's balanced. If it equals the same, then that means the sum of the torques is what? 0.
Wow.
Because when forces are balanced, Logan, the net force is 0. When you have a balanced seesaw, the net torque is 0. But notice what happened, guys. If you made the mass bigger, what do you have to do to the distance?
Decrease
Shorten
it.
Can you have a pen I can use?
Okay, so if you have a lighter mass, you need a bigger distance.
You need a pen?
If you got a, no, it's multiplied by it right here. Your distance is your how far it is from the middle. This is weight, so you know how to do weight, mass times gravity. All right, and what would be the angle that the pennies are pressing on the ruler? 90 degrees. What is the sine of 90 degrees? 1.
Get it even, equal.
Okay? Yeah, the radius is from the middle, Christopher. So, from the 50 to the 4 pennies, how far is that? 0.1 meters. Okay, the other penny, the 1 penny, how far is that from the middle? All the way to the end? So 0.5. Okay? So, 0.0025 kilograms times gravity times 0.5 meters. So your torques should be the same. No, Riley, it didn't work out? Should work out. They should be equal on both sides, right?
Perfectly.
I mean, if they balance, yeah.
Yeah.
All right, so the torques balanced out, the sum of the torques was 0. You sure you're all right, Mariano?
F times R.
Okay. What would happen if you moved the 4 pennies out more? It would create an unbalanced torque. Okay, you would have more torque on one side than you do the other.
It would spin the one side.
You did. You just forgot a variable. Christian Leitner, if you moved, okay, let's say the desk wasn't there and this was sitting, just floating in space, and you moved the pennies to one side, the 4 pennies to one side. One side would generate more force, right? It would begin to spin, correct? So in order to spin something, you have to have an unbalanced torque. If you have a balanced torque, it does not spin.
Right.
Yes, Mr. Ryan. Yeah, I'm sorry, man. I know it's kind of bent. My bad. It's okay. We got another activity. Got another activity. Is you ready? Okay, so that was just a demo. Second demo. I want you to measure the length of your foot from heel to toe.
Here we
Set.
go.
With our shoe on, or
You can if you want. You don't have to.
My shoe on,
what do you take the shoe off? I don't want to smell the room.
Length of my foot, what?
The whole length. Bottom of it.
Just measure my foot.
31.5 centimeters.
Measure your foot.
Okay. So who's let's use Alejandro's.
What size are you wearing?
Your partner may well let's use Ross's. Centimeters, please, centimeters. What's your Ross? 32 centimeters? Alright.
And Logan, what size are you wearing? What size is it?
Would you believe?
centimeters or 2.5.
Don't take your shoes off.
Yeah, right. You don't have to take your shoes off.
It's not bad.
Oh, these are 11.5.
Mine are 10.
Okay.
Okay, so I'm size and half.
Is your foot a seesaw?
Yes.
Yes.
It balances us.
Your foot is a seesaw.
Seesaw.
Okay? What is the central point that your foot is balancing around?
Your leg.
Which part?
Your ankle.
Heel.
Your ankle.
Yeah.
Go
So your
Panthers.
ankle bone is just like the marker on your desk.
30 centimeters.
Now what I want you to do is measure the distance from your ankle to your heel. It might, you can take the shoe off, it might make it easier, but from the ankle to the heel, just the ankle to the back of the heel. What is that distance? So if 32 centimeters was Ross's whole shoe, from toe to heel, what would be from ankle to heel?
Oh, like 7.
Oh, no, it's about 29.
No, not up the leg, from ankle back to the heel. Back to the
No.
heel.
Back of the heel.
The
From
back of
ankle
your-
to the back of the heel. Not ankle up the leg, not ankle up the calf.
From here to here.
Back.
Here to here, James. Not this way.
29 centimeters.
It is not 29
No,
centimeters.
he's talking about his regular foot.
Your regular foot's
Yeah, that's
29
what I said.
centimeters. Okay. So from ankle to the back of the foot. Not ankle up the leg, not ankle up the calf, backwards.
Yeah.
Wait, the ankle to the calf?
No.
Ankle to your heel.
What is that, Ross?
Oh, mine's 10.
8 centimeters.
Mine too.
Where's my ankle? I got an ankle.
Okie dokie. So what happens is, when you run, when you jump,
Hey.
you have a seesaw that pivots around your ankle. What is making the thing move like this?
Good guy.
What makes the foot point down?
8.
Your other foot.
Come on, let's think about this. What on your body makes the foot point?
Is it the same size?
And what is your calf muscle attached to?
Your ankle.
Your
Bone.
Achilles tendon.
Your
I thought the big toe keeps you balanced.
So the Achilles tendon is attached to the heel. Okay? So here's what we're going to do now. We are going to calculate how much force your muscle, it's more than your calves. Your calf, your hamstrings, your butt, your back, the whole kinetic posterior chain allows you to do this.
What? So everything on the back end makes
So I want you to stand on your tiptoes, and we're going to calculate how much force there is really on your heel that allows you to do this. Okay? So, go ahead and try it. Go ahead and stand on your tiptoes. And I want you to observe, which way your heel points. Which way does your shoe point? Top of your back of your heel, right here. When you stand on your tiptoes, what angle is it pointing at?
45.
It's not straight up.
It has on like 45.
Is it 45?
Probably more.
Look at the back of your heel. It kind of digs into your Achilles, doesn't it?
what angle am I at?
Shorty's coming. They flop down.
Well, you guys estimate it. You tell me.
45.
No, that's like.
What do you think, Ross? Look at the back of your shoes.
About 30.
Like this?
What you say is about
What am I at?
30.
You got a
You
protractor?
think so?
I will
30?
go all the way up.
All right, so if you had all right, stand flat-footed. So that's perpendicular, okay? Now stand on the tiptoes again. So let's go back this way.
Oh, 35.
Relative to perpendicular, how much is that?
35.
About 30 degrees?
35.
About 30 degrees?
35.
Okay.
Do 35.
30 degrees. is good. So that means that's pulling at 60.
Oh, no, I just.
60 internal.
Chris, you got 180.
No, not 180.
His body is like 40.
That would mean your heels were on your toes.
All of his.
Okay. So, zoom in, take a picture of the board. I drew a rough drawing of the foot. What do you think? Any good?
That's fine.
Okay.
Very good. You should have gone and made your master's in art.
No. I think I'm not as good as the minute physics guy. That was just a shoe, guys. So anyway, so this is what it is. Distance from the toe. Excuse me. This distance 1. I misdrew that. This distance 1 is the entire length of the foot. Okay. And the distance 2 is just to the heel. All right. So for example, now Christian, Ross, if your whole foot was 32, right? Your whole foot was 32?
Yes, sir.
And this dot's your ankle, and that was 8. Then how far from the ankle to the toes? All you gotta do is subtract. How far is that? What's 32 minus 8? 24? So from the ankle to the toes is 24. Okay. Now, if you stand on your tiptoes, you are pivoting around your ankle. You're also pivoting on the balls of your feet. But your Achilles is pivoting around your ankle. The foot is moving around the ankle and it's doing this. Well, what's pulling? A humongous force here. So now we have to use our angles. Okay? So you have your weight pulling down. I want you to calculate your weight. Do your pounds to kilograms. Look up on the Google machines.
I'm 73 kilograms.
Okay, and then calculate it in newtons. So for me, let's see. I can get on the Google machines, and I can go pounds to kilograms.
Oh,
Pounds to kilograms.
I'm 72.57.
What are you on?
72.6.
Right in nurse's tag.
62.59.
Okay,
62.59.
and then 86 kilograms. So 86 kilograms times gravity, and if I wanted pounds to newtons, I can cheat.
When? Is that next? No, 2 weeks.
2 weeks. From
That
Oh,
would be the
doesn't have a
the
converter.
7th. No.
7th of November.
Second week of November. So Friday is November.
Yeah, and then
Okay,
next Friday would be.
guys,
So it'd be the
calculate your weight.
Wait,
Logan,
is that the second week?
calculate your weight.
Second, third?
Christian, calculate your weight.
My weight is 70.
I got 62.59 kilograms.
72
That's your max. Calculate your weight in newtons.
Times.
Oh, plus
I'm
9 point,
pretty
or times
freaking
9.
large.
Times 9.8. You're pretty freaking large.
612.
I don't know why things aren't revolving around me.
Ooh.
Gosh,
How many numbers is you?
I would love to be able to just
Only
3,000.
if you stop thinking.
I'm 711 newtons.
And they just wants to know what the revolver is.
Wait, 711.
86 times 9.8. I am
You can tell.
843 newtons. Okay. How much force is needed to lift me off the ground?
Ooh.
A lot.
55
If you're standing on your
horsepower.
tiptoes, are your torques balanced? Are you balanced? If you're standing on it, you're balanced.
Yeah.
Okay, so write this down. Torque 1 equals torque 2. Torque 1 equals torque 2. Write that down. I'm gonna change that to 30
Oh, we
degrees.
got that tapping thing Thursday.
Torque 1 equals torque 2. Okay.
No, this says like 31st.
What is the definition of torque? Force times the distance times the sine of theta. So on this side, force times the distance times the sine of theta for 1 equals force times the distance times sine of theta for 2. Remember, they're balanced, they're equal. Write that equation down, Alejandro. Write that, Christian Lane. Write that, Christian Lane. I really would like you to participate in writing this. We're going to use Ross's data here, okay?
Okay.
All right. So from Ross's toes to ankles, his distance was 24 centimeters. Okay? So that would be this one. Now, Ross, do you have your weight in newtons?
Yeah, 754.6 newtons.
755 newtons. Okay.
Yeah.
So Ross is 755 newtons. So he's 755 newtons, and from toe to heel, it's 0.24 meters. Now, if he stands on his tiptoes at 30 degrees, it's 90 degrees plus 30 degrees. What is 90 degrees plus 30 degrees?
120.
Okay, get the sine of 120 real quick. Can you do it? Can you do it, Greeny? Sine of 120?
0.8.
Okay, it is possible. So it's a sine of 120 degrees. You understand, Ryan? Tiptoes. Not 90 degrees anymore. We're 90 degrees plus this. On the other side, from ankle to heel, it's only 8 centimeters, but we don't know what that force is. Leave it as force 2. So 0.08 meters. Okay? And the heel, as you notice, the shoe pointed back at 30 degrees, right? It pointed back at 30 degrees, so it's now sine of 60 degrees. Okay?
Where you
Not
get
an obtuse angle anymore, it's acute.
Where you get the sine 120?
Wait.
90 degrees into the floor plus the 30 for the angle of the foot. Where does your weight have to go? Straight down.
Gotcha.
Okay. So now what I want you to do, guys, is I want you to solve for force. Okay, I know it's a lot. Okay. 755 times 0.24 times. Oh, you got to be in degrees, Greeny.
I need that. That's
Oh,
one.
good job. You need a calculator, buddy.
You need to be in degrees. We're back in degrees today. Sorry, folks.
Did you get Ross? Did you get a big number? Oh, crap.
Okay, so your muscles, your calf, your hamstring, and your butt have to lift with a force of
2,273 newtons.
2,273 newtons. Now here's what I want you to do. We're going to convert it back into pounds. You ready?
I didn't get a number that big.
Oh yeah. Well, you got 1,000 something.
I want to know what the degrees of the degree.
I got
Okay.
156.
Every pound has 4.448 newtons. So divide that by 4.448. Ross.
Yeah, I didn't get a number that big.
I want to know why are the signs,
Whoa!
the degrees on the side,
511 pounds.
what they are?
511 pounds?
Sir.
Correct.
I didn't get a number that big.
So your muscles are pulling with much more force than your weight in order to get it to move up. Think about it. Can you jump?
Yeah.
What kind of force do you think you would need in order to make yourself jump?
A lot.
Much more than your weight. Can you run? What kind of force would you need to go make yourself run? Much more than your weight. Much more than your weight.
So does that mean?
So that is a tensional force. So yes, it's a raising force, and it's also the tension in your muscles to keep you up like this. Yes.
So when we said that like you weigh different spots on Earth, not like this as you can do, but
This is a calculation of the force on your muscles pulling your body up.
so it's not like how much.
This is not how much you weigh. This is the applied force on your muscles keeping your body up like this.
Man,
Yeah, there's a lot of physics to the human body. Yes.
Where it says, like where the in the formula where the degrees are.
Yes.
Each sign. Where do they come from?
This
Yeah.
here.
Oh, the sun. But it said 120 degrees.
Right. It's 90 degrees, weight into the floor, plus the 30 degrees of us standing on our tiptoes. What's 90 plus 30?
Okay.
So this whole angle, Christian,
Where does the 60 come from?
here,
Oh,
that's your shoes pointing back. This is this.
Okay.
This
I
is
thought
this.
You were comparing the foot.
No,
The
no.
other foot.
So Logan, this would actually, I mean not Logan, but Christian Leitner. So relative to this horizontal, it would be 30. So that means it's less than 90. It would be an acute angle.
Right.
So that means every time you do calf raises.
Yes,
weight-
you are lifting weights. Is your body a weight? It is a weight. Can you get strong with just doing on the body stuff?
yes.
Yes. Do boxers and martial artists get very strong doing on the body lifts?
Yes.
Yes. Do wrestlers get very strong just working with body weight?
150.
Absolutely.
And then.
Do you need to go to the gym and squat 500 pounds in order to be functionally strong?
No.
No, you don't.
Oh,
Okay? At some point, NFL football players quit lifting weights because it doesn't do them any bit of difference between squatting 700 pounds or squatting 800 pounds. At that point, it becomes functional strength and how they're able to move.
So we would take whatever.
If you're going up 30. If you're going up
Yeah.
30.
I know a dude who put on like 60 pounds of straight muscle in one summer because he built like just a body core thing.